At high substrate concentrations, if S is big, then what happens is we can use a simplifying assumption. If S is big and Km is just whatever, small compared to S, then Km drops out, right? Km is negligible. And then the two S's cancel. And so at very high substrate concentration, this becomes zero order in S. At very low substrate concentrations, then Km is big and S drops out. If Km is much bigger than S, then the S is negligible, and this becomes first order in S. And so in the Michaelis-Menten equation, we can see this interesting behavior in enzyme kinetics. You aren't going to have to derive this. Let's just did this because there's a lot of biologists in the class. All right, that's pretty much chapter 14. So chapter 14, we looked at things like, how much, how long, and what happens to the rate. And then we looked at mechanisms, getting some insight into mechanisms based on the rate law that's observed. Kinetics and thermodynamics are related. Thermodynamics just looks at the before and the after, the delta H's, the delta S's, and that kind of stuff. But what we're going to do is we're going to go on to chapter 19 next, and let me just tell you what you need to review. You need to review things like delta H, delta U, Q, W, Dalton's law, Avogadro's law, constant pressure, constant volume, right? All those things. Because we're going to use a lot of that in chapter 19. What chapter 19 looks at is the driving force for reactions. In Chem 1A, we just said the driving force is going from less stable to more stable. That's it. Less stable is more reactive. More stable is less reactive. And so we're looking at the driving force for reactions. But that works most of the time, but there are some times where we go from less stable, less stable to more stable. In physics, let me do this example. In physics, we're always going from higher energy to lower energy. So this would be gravitational potential energy. And this would be the driving force here, just going lower. But in physics, would you ever see this? Would you ever see the pens go from lower energy to higher energy spontaneously? No, you don't have to look at the ground for things shooting up and hitting you unless they're projected by something. You just look for things that are going to fall on top of you, right? Well, in chemistry, sometimes we have reactions that go from less stable to more stable. Sometimes we have reactions that go the opposite, more stable to less stable. And so let's look at an example of that. So ammonium chloride solid. Ammonium chloride solid, if we were to dissolve that in water to form ammonium chloride AQ, then this reaction has a driving force. It's actually a physical process, it's just dissolution. But when we look at the delta H for this, the delta H is greater than 0. It's endothermic, which tells me this. That tells me that ammonium chloride solid is more stable than ammonium chloride AQ because this is going to require energy. And so what happens is when you dissolve ammonium chloride in water, it gets cold rather than hot because it's endothermic. Well, what's driving this? This would be like the pen, shooting up here. What's driving this? Sometimes there's no change in energy at all, and yet it happens. There's another physical process. Oops, sorry. There's another physical process that happens, and that's mixing of two ideal gases. Let's say I have a container here. On the right side, I have gas A, which is black. And then on the left side, let's put gas B to make red. And so right now they're segregated, but if I just let this, eventually what's going to happen is the gas A and gas B are going to mix. Let's call these ideal gases. And let's look at the energy. What's the total energy of an ideal gas? Well, the total energy is called its internal energy, right? And so the internal energy is given by the symbol U. What does total energy consist of? Total energy consists of what we call potential energy plus kinetic energy. And so we look at the total energy before and the total energy after. Well, if this is an ideal gas, there's no potential energy because there are no bonds. Potential energy consists of bonds, intermolecular forces, that type of stuff. And so in an ideal gas, this is zero, so the total energy just depends on the temperature. And so let's have gas A at 25 degrees C, gas B at 25 degrees C, and the mixture at 25 degrees C. And that means that the change in the total energy is equal to zero for this process. There was no change in energy. If there's no change in energy, then why should the mixing take place? Shouldn't it just stay as is? No, there was a driving force. And so what it means is that energy is not the only driving force in nature. It turns out that there are two driving forces that we're going to be looking into, and the two driving forces, one, we want to minimize energy, so that's always good, going from high energy to low energy. Energy can be internal energy or enthalpy, and two, we want to maximize S. S stands for entropy, and S is a measure of disorder in the system. And so we want to maximize the disorder in the system. And so these would be the two driving forces in nature. And so we can see what's driving this reaction, what's driving this, well, this mixing is entropy. It's becoming less and less ordered, because before it was ordered, you had all the red molecules on the right, all the black ones on the left. Now they're all mixed up. And so that's actually increasing the entropy. And so the energy is not changing, but the entropy just increased, and that's going to drive this reaction. And so when we look at reactions or processes, now we have to think both in terms of energy and in terms of entropy. And so first off, we're going to do this qualitatively. If we look at the entropy of a solid versus the entropy of a liquid versus the entropy of a gas, which one should have the highest entropy, the highest degree of disorder? The gas. So the gas is, let's say all these are at the same temperature. And so this gives us a way to make some predictions. So if we're looking at calcium carbonate solid plus 2 HCl's, this is going to yield calcium chloride plus H2O liquid plus CO2 gas. Do you know, is this reaction exothermic or endothermic? This reaction is acid-base reactions. Typically, we're going from stronger acid to weaker acid, therefore it's got to be exothermic. And so this is exothermic. We know energy is going down. And so this is what we call a driving force for reaction. Now, let's look at what's happening with the entropy. Is it becoming more ordered or less ordered, going from reactant to product? It's going to become less ordered, because here, this is aqueous, this is aqueous, this is a solid crystalline. And so and we got that gas, so this says reaction. And so both of these say reaction, and so we expect reaction. There should be good driving force for this. And so both agree here. We should get a reaction. But there are other cases, like for example here. If we look at ammonium chloride solid going to ammonium chloride aqueous, then we look at delta H. Delta H is positive. If delta H is positive, that means energy says we shouldn't have reaction. You know, it's a no reaction. But delta S, entropy is going up, so that says reaction. And so which one wins out in this case? Well, which one won out was reaction. We observe reaction. Ammonium chloride soluble in water. But what if we take this? Let's try to dissolve magnesium carbonate solid in water. If we dissolve magnesium carbonate in water, we'll form magnesium carbonate aqueous. Well, this is going to be endothermic. So we've got to break apart that lattice. So, you know, endothermic says no reaction should take place. But the entropy is going up because magnesium carbonate AQ should be a heck of a lot more disordered than magnesium carbonate solid. And so this says reaction. And so which is it? Is it no reaction or reaction? Well, in this case, it's no reaction. And so how do we know which one wins when there's a conflict? If both agree, let's say energy says no reaction, entropy says no reaction, then it's easy. There's going to be no reaction. Or energy says reaction and entropy says reaction, then it's easy. But when there's a conflict like this, which one wins? How do we tell and the thing is, we can't do this qualitatively. We must quantitate delta S. In other words, we have to calculate delta S. I'm skipping delta H because I assume everybody knows how to calculate delta H. Right? Is there any problem in calculating delta H or delta U? No, it should be easy, right? It should be easy. But what about delta S? How do we calculate delta S? Well, calculating delta S is easy too. In order to get delta S, all we need is the entropy of the products minus the entropy of the reactants. Just sum it up. These are called absolute entropies. Just like we did for enthalpy. Did we do that? We just took the enthalpy of the products minus the enthalpy of the reactants? Is that what we did? No. We took the sum of the enthalpies of formation, the delta H's of formation. We didn't do this. Absolute entropies were not determined. If you recall, it was the delta H of formations that were determined. Why weren't absolute entropies determined? Enthalpies, sorry. Not temperature. Temperature's easy. Why were enthalpies, absolute enthalpies, not determined? Well, what is enthalpy? What's the difference between enthalpy and internal energy? See, these are the things you have to have clear in your mind, because thermodynamics is actually a pretty challenging topic. And the reason it's challenging is because most people don't know the definitions of all these things. And so as you progress in thermodynamics, you get more and more symbols. And so they have thermodynamics classes for every major. They have thermodynamics for biologists, thermodynamics for engineers, thermodynamics for physicists. And so as you go on, you get more and more symbols. And if you don't know the definition, because the definition will tell me, you know, For example, is it okay to use delta H under constant pressure conditions? Is it okay to use delta H under constant pressure conditions? Yes or no? Yes? Under constant pressure? Yeah. Is it okay to use delta H under constant volume conditions? No, unless what? Unless there's no gases generated or gases consumed or something like that. And so it's easy to make a mistake, because if you don't know the restrictions on delta H, if you don't know how delta H is defined, you could mistakenly use the wrong equation under the wrong circumstances. And so over here, we don't know the absolute enthalpies. Absolute enthalpies, sorry, not enthalpies, enthalpies. Just like absolute internal energies were not. You know, U final minus U initial. We never used this, right? The reason we never use that is because absolute internal energies are not easy to determine because of what? Kinetic energy is easy. This is the problem of the potential energy, because there's energy stored in bonds, right? There's energy stored in bonds as potential energy. There's energy stored in electrons. There's energy stored in the nucleus. Is there energy stored in the proton itself? Yeah. And where do we stop? You know? And so the potential energy is very difficult. That's the problem. But absolute entropies can be determined, unlike enthalpies and internal energies. Almost done. And so how are they determined? There are two ways that they're determined. We can calculate them using the Boltzmann equation. The Boltzmann equation is on Boltzmann's headstone. You can see it above his, there's a picture of it. You can see it above his head, the statue of his head. But the absolute the absolute entropy is equal to K, the Boltzmann constant. This is not the rate constant. This is the Boltzmann constant, which is different. The Boltzmann constant is just R, the gas constant, divided by Avogadro's number. And so it's the gas constant not per mole, but per molecule or per particle, times ln of W. W is the number of ways to arrange things. And so let's say there's only one way. If W is equal to 1, only one way to arrange it. And so everything has to be in its perfect place. Well, the only way to get that is like this. In real life, we would have to have a perfect crystal, no defects, and there can't be any movement. Is if there's movement, then there are different positions that we can position the atoms or ions in. And so it's got to be a perfect crystal at 0 Kelvin. And then there's only one position for each of the species. And so if there's only one way, then what is the entropy? The absolute entropy. Well, it would be ln of 1. Ln of 1 is 0, and so the entropy would be 0. And so the perfect crystal at 0 Kelvin has 0 entropy. And so this would be something called statistical thermodynamics. And so what you do is you figure out the number of ways. So let's say you had 5 coins, and you figure out how many ways you can arrange the 5 coins, heads, tails, right? And that will tell you the entropy of that system. Okay, the other way we can determine absolute entropy is by experiment. It turns out that the entropy is related to heat capacity. So for example, water has a very high heat capacity compared to something like copper. And so why would water have a high heat capacity, copper have a much lower heat capacity? Well, it turns out water has a lot of ways to absorb energy. What are the ways to absorb energy for water? Well, water can rotate, it can vibrate, it can translate, right? Has a lot of different ways. Whereas copper can only vibrate. And in quantum mechanics, there are what are called allowed vibrations and forbidden vibrations. Not all vibrations are allowed. And so entropy is related to heat capacity. So by measuring heat capacities at different temperatures, we can determine the entropy, S. We have to measure the heat capacities as close to 0 Kelvin as possible. And so here's the temperature, here's the heat capacity, here's water. And so solid ice has a fairly low heat capacity. And then when that ice melts, what happens to the heat capacity? It shoots up. And so liquid water has a very high heat capacity. But when that liquid water vaporizes into gas, what happens to the heat capacity? When the liquid water vaporizes into gas, the gas doesn't have a very high heat capacity. I forgot. It's close to solid, like this. And so here's solid, here's liquid, here's gas. And so what has the higher entropy? Gaseous water or liquid water? Well, gaseous water has a higher entropy. So how does the entropy work? The entropy is going to work like this. If we look at the entropy of a solid is going to be low, and then it jumps up. The entropy for liquid is going to be much higher, and then it's going to jump up again. The entropy for gas is going to be higher. So this is the absolute entropy for water versus temperature. This is going to be solid, liquid, and gas. And so the way this works, the mathematics of this is this. The entropy is going to be the area under the heat capacity curve. In other words, it's what we call an integral. And we integrate it from 0 to the temperature of interest. So if we want the entropy at this temperature, we would take the integral of this. That is, we'll get the area under the curve from 0 to t. And this total area is going to be our entropy here. And so if we want the entropy of a gas, even though the heat capacity of the gas is much lower, we have to integrate this. That is, we get it from 0 to this t here, the total area under the curve. And so the gases are going to have a higher entropy than the liquids, which have the higher entropy than that. And so by taking heat capacity measurements, and we'll look at the math a little bit later, we can figure out the absolute entropy of water at any temperature here. Once we know the absolute entropy, then we can just plug it in. You know, delta S is equal to S final minus S initial. And we can calculate it. And so the calculation for delta S is very easy. We just get the entropies that somebody else measured and use those. Okay. And so what you have to do is you'll have to do some review of chapter 7. And then we'll be good for chapter 19. Okay.